We doing it. It's the fundamental theorem of calculus. This is a big deal. It sounds like a big deal because it is, but actually it's more or less the same as what I called last time the total change theorem. Remember what I wrote last time? It was integral from a to b of f prime of x dx is equal to f of b minus f of a, right? This says the integral, the area under the curve of the derivative is equal to the initial value, the final value of the function minus the initial value of the function. All right. Why this is true is a little complicated. You got to watch the video from last time. All right. But anyway, this is basically the fundamental theorem of calculus. But typically, it is not written in this way. In this way, we have this function here, and we have this original function and its derivative. But another way you could say that is this is a function and this is its antiderivative. So more commonly, we're going to write it in this way. When the big F is the antiderivative of the little f, then we have integral a to b little f of x dx equals big F of b minus big F of a. All right, put that in a box somewhere. This is called the fundamental theorem of calculus. And it gives you a very easy way to figure out what the actual answer of the integral. You know, everything we've been talking about so far has been estimating the area under the curve, but this actually tells you exactly what it is. The area under the curve of some function equals the antiderivative with the final value minus the antiderivative plugged in with the initial value. That's all there is to it. This is actually a very easy way to find the true area under the curve of a curvy function. This is the fundamental theorem of calculus. It's big news. And this, finally, is the connection between the area under the curve and the antiderivative. Or if you like this big F basically is the indefinite integral. This is why the area under the curve, the definite integral, is so closely related to the antiderivative, the indefinite integral. This is the relationship. Let's just do a bunch of examples. How about my favorite example, the integral from 0 to 1 of x squared dx. As an area, this represents, x squared is a parabola here. It's this area from 0 to 1. Do you remember when we first started talking about the definite integral, the area under the curve, I used this as an example. What is the area here? I told you the true area here, and I just asked you to take my word for it. It is 1/3, but how do you figure that out? Actually, you can figure it out using the fundamental theorem of calculus. In my opinion, it's a bit of a miracle that this area turns out to be 1/3 because it's such a weird shape, and there doesn't seem to be a good reason that it should be some simple answer like 1/3. But it is actually the reason you might say is because of the fundamental theorem of calculus. Okay, in order to do this, so the answer here, because of the fundamental theorem of calculus, will be f of 1 minus f of 0, big F's, where big F is the antiderivative of x squared. All right, and what is the antiderivative of x squared? We can figure that out. Or we already know how you find the antiderivative. Remember, a couple weeks ago, you increase the power by 1, and then you divide by the new power. So it is 1/3 x cubed plus c, right? Now, it turns out when you're doing the definite integral like this, the plus c ends up being totally irrelevant. You're about to see why. So that means integral 0 to 1 of x squared dx is big F of 1, I'll just write this again, minus big F of 0. What is big F of 1? I plug in right here. I get 1/3 times 1 cubed plus c minus big F of 0. I get 1/3 times 0 cubed plus c. What happens here when we simplify? 1 cubed is 1, so that right there is just 1/3 plus c minus 0 cubed is 0, so that goes away entirely. And this is just going to be c. So c minus c will cancel. And I just get 1/3, which is what I told you before is the true answer. Now do you believe me? I hope you believe me now. It is 1/3. And do you also believe me that the plus c doesn't actually matter? In any problem like this, when you're subtracting these two things, as you do in the fundamental theorem of calculus, The c's will always cancel because the first time around you get a plus c, but then you're subtracting and you get the same plus c here. When you distribute the minus sign, it'll turn into a minus c, and the c's will cancel. So when you're doing this, can I just say, I'll write it over here. When you're using the Fundamental Theorem of Calculus, you don't need to do the plus c. Certainly the plus c does not appear in your answer, but you don't even need to put it in there in the middle steps, because it will always cancel by the time you get to the end. So we're not even going to bother with the plus c when we're doing the Fundamental Theorem of Calculus. Now, this procedure here, as I've written it, is a little cumbersome just because you begin by writing this, and then you have to say, like as a little sidebar, I'm going to figure out separately what the big F is. And then once you figure that out, you go back to the beginning, plug that thing in here, and you get your answer. This is a little cumbersome to write in this way, going back and forth. So there's a special notation that we're going to use for using the Fundamental Theorem of Calculus. So I'm going to write the same process, the same problem, but just writing it in a different way, which avoids this kind of back and forth, flipping back and forth to find the antiderivative. Here's how we are going to write that same problem. Integral from 0 to 1, x squared dx. Here's how we do it. Right here, immediately, I am going to find the antiderivative of x squared, and it is 1/3 x cubed. I'm not going to write the plus c because, like I said, in a problem, when you're doing a definite integral, the plus c's never matter. And how do I indicate this? The integral is going from 0 to 1. In order to indicate that, at this point, we're going to put this bar and the 0 and the 1. So what I did in this step was I got rid of my original function and replaced it with the antiderivative, and also didn't write the dx anymore. And instead of the integral sign, we're not doing any integral anymore because I just did the indefinite integral. I just did the antiderivative. But we still need to indicate somehow what these numbers were. So the way we carry that forward in this notation is just the bar and the 1 and the 0. So the meaning of this bar here, this means, I just realized you can't see that. Sorry, there's a 1 up there. I just put these two numbers on the bar like that. The meaning of this bar is, in the next step, I will plug in 1 and 0 and subtract. All right? So you write the bar to indicate that in the next step, I'm going to be plugging in 1 and 0. All right, and now let's actually do it. So next step, you actually plug them in. I got 1/3 times 1 cubed minus 1/3 times 0 cubed. You go through this whole formula, plug in the top value everywhere, and then you go minus, and you plug in the bottom value everywhere. And then you simplify if you want to, I suppose. This is just 1/3, right? For all the same reasons we said before. So this is the way we're going to write it when we do definite integrals using the Fundamental Theorem of Calculus. First step, you find the antiderivative, and you put the bar just to remind yourself of what the two values are, and then you plug those two values in. Plug the top one in first, then subtract, plug the bottom one in. That's how we do it. Let's just do a whole lot of examples. I got 3 examples. You'll see, actually, these are pretty easy once you know how to do it. Let's do the integral from 2 to 6 of x squared minus x plus 4 dx. So whatever this function is, it has some area under the curve when you go from x equal 2 to x equals 6. That's what we're finding here. And remember how we do. We, first of all, take the antiderivative. I get 1/3 x cubed minus 1/2 x squared plus, what do you do with 4? The antiderivative of just a constant, remember, is that same constant times x. So 4x. And then I'm going to indicate with the bar, I intend in the next step to plug in 6 first, and then subtract, and then plug in 2. All right, let's do it. For the 6, I go through the whole thing, plugging in 6 everywhere for x. It is 1/3 times 6 cubed minus 1/2 times 6 squared plus 4 times 6. That was when I go through and plug 6 in everywhere. And now I go minus, put parentheses, haters, you better put parentheses, and then plug in 2 for x everywhere. I get 1/3 times 2 cubed minus 1/2 times 2 squared plus 4 times 2. And that's my answer. As usual, you could plug it into your calculator if you want to. I don't care about that. This is how we do it. This is how we find the area under the curve, the definite integral. It's not so hard, right? Here's another one. Let's try integral from 1 to 2 of 1 over x dx. All right. On a picture, this would represent, 1 over x. The graph looks like that. And I guess it's this area right here. From 1 to 2. What is that area right there on the graph of 1 over x? Did you ever wonder? Probably not, but here we're going to do it anyway. We immediately begin by taking the antiderivative of 1 over x. Do you remember the antiderivative of 1 over x? It is natural log of absolute value x. And then I put the bar with the 1 and the 2. The bar means plug them in. So I get natural log of 2 first. The absolute value of 2 really, but absolute value of 2 is 2, right? Minus natural log of 1. There you go. You can plug these into your calculator. Perhaps you remember when we talked about logs, the natural log of 1 is always 0. So this really, the answer is just the natural log of 2. All right. One more example. This is not really any more difficult, but just to demonstrate a particular point about how the definite integral works. Integral minus 3 to 0 of minus x squared dx. Now on a graph, what this looks like, x squared is the usual parabola going up. Minus x squared would be the upside down version of that. So this is minus x squared, and I'm looking at the area from minus 3 to 0. So it would be this area right here. All right. You're going to see that the answer here will end up being a negative number. This is a little weird because everybody knows that the area of something is always a positive number. But when you use the definite integral to measure the area, it actually comes with a sign that is positive or negative. Area above the x-axis counts as positive area. Area below the x-axis counts as negative area. And if there's some mixture, it'll like add them together and some it will like cancel out a little bit. Anyway, this we should expect to get a negative answer because this picture consists only of negative area. Let's just see what happens. We do the antiderivative. We get minus 1/3 x cubed, plugging in 0 and minus 3. We plug them in. Minus 1/3 times 0 cubed minus 1/3 times 3 cubed. And what is that? That's just 0, right? This over here, the minus and the minus, minus 3 is what I'm supposed to plug in. I got worried there a little bit. Minus 1/3 times minus 3 cubed. All right, the minus and the minus here will cancel, and I get 1/3 times, what is negative 3 cubed? It is negative 27. Negative 27 divided by 3 is negative 9, right? Negative 9 is the answer. So the answer of this definite integral, it equals negative 9. That means this area is 9, right? The area is 9. It's just below the x-axis, which is why it comes out of the integral as a negative number. All right, I got one more. This one is interesting because you must do a U substitution. Can we do the fundamental theorem and also use U substitution? The answer is yes, you can. What you do is you do the whole U substitution first, ignoring the numbers here, and then finally at the end you plug in the two numbers for x. Let's just try it. There's not much to do. There's really not much to it, but we ought to do an example. This one here, we have to do the U substitution because I have a weird thing inside of another thing. The 25 minus x squared is inside the square root. That's what I'm going to choose to be my U. 25 minus x squared. Then du is, remember, du is you take the derivative of u. So the 25 goes away. Minus x squared becomes minus 2x. And then you always include dx as part of the du. All right. Remember how to do the U substitution? I hope so. Come here, try to plug stuff in. First, I'm going to begin by putting the U in where it is, under the square root. Now, for the next few steps, I'm not going to write the two numbers in the integration. It's because I'm changing everything to u's. These refer to values of x's, but I'm changing everything into u's, which will slightly mess these numbers up. It's going to be fine in the end. Like I said before, we're going to do the entire U substitution, and in the very end, we plug in the 5 and the 0. Okay, what do we get? Here, I'm going to continue trying to substitute, so I'll move the u part to the beginning, root u at the beginning, and then followed by x times dx. And then what did we do with x dx? I see that right here. We can divide this constant over there. Minus a half du equals x dx. So that's what I'm going to put right there. square root of u times minus a half du. And then we pull the constant out. This is a very standard u substitution. I'm also going to write square root of u. I'm going to write u to the 1/2, just like we always do, times du. All right, I'm finally ready to do the integral. I've replaced all the x's with u's, and so we can do the integral. I increase the power by 1. It becomes u to the 3/2. And then I have to divide by 3/2 in the front, which is the same as multiplying 2/3. Like so. All right. Ordinarily, I would put the plus c here, but since I'm doing a definite integral, the plus c is not necessary. It will cancel every time you do this, so I'm not even going to write it. Last step of the u substitution is to replace the x's where you see the u's. So this becomes minus a third. U is 25 minus x squared to the 3/2. All right, I have done the complete u substitution. Remember what I said? I was going to do the whole u substitution, and then at the very end, plug in the numbers 5 and 0. Right here, I'm going to write the bar with 5 and 0. Right? Let's do it. Plug them in. First, I go through here and plug 5 in for x, minus 1/3, 25 minus 5 squared to the 3/2. And then minus, I go through again and plug in 0 for x, minus 1/3, 25 minus 0 squared to the 3/2. There you go. That's the answer. You plug it into your calculator if you want. Actually, this one is not so hard to do by hand. 5 squared is 25, so 25 minus 25. That's all going to be 0. And then over here, this is 25 to the 3/2. Really, I get 1/3 times 25 to the 3/2. What's 25? What's a 3/2 means? The square root and then do the third power. So the square root here is 5, and then you do the third power is 125. So this is actually 125 over 3. Do you care about that? I don't know.